When people hear the word robot, what actually is a robot and what's not a robot?
Well, the RIA definition is a three-axis machine that's programmable, and that's really the classic definition of robotics is a programmable multi-axis machine that can repeat the same tasks over and over. You see a lot of these little remote controlled cars and things like that. You know, the robot fights, you know, that you see in the first robotics and things like that. That is not, those aren't really the classic robotic. They don't go by the classic robotic definition. They have somebody driving them around and things like that. So in industrial robots, it's a multi-jointed arm that is programmable and can be used over and over again for the same task.
So where does the real value as far as an ROI come in when companies decide to use a robot?
Yeah, it's quite extensive. First of all, you're applying technology that will make sure that the operation, if it's applied correctly, will be very, very consistent. So what throughput you get will be very consistent. So if something changes in the process, it's easy to identify what that is and correct it. Also, many of these operations are jobs and processes that people injure themselves on. You know, you get this repetitive injury syndrome, and they're very difficult for people to do. They're usually many times in environments that are not very appropriate for people to be in. So as a result, injuries go down. Right. And also the fact that you can apply a robot 24 hours a day, lights off, in many cases. Right. So I mean, there are many benefits on top of that, but I could go.
So as we see over time, and obviously the auto industry has been using robots for a long time, but how has robot use changed over the years?
Well, we're applying it to things that weren't thought of in the past, and that's because the software that we use and the ability to have sensory input into the robots is getting very, very sophisticated. You've heard of Moore's Law. You know, every 18 months, technology doubles, and that is very true.
It's true in robots?
Absolutely it is. We're seeing it all the time. So the CPUs are getting faster. I/O is not a problem anymore. It used to be in the old days, you know, you got 8 in and 8 out, or 16 in and 16 out, and now it's many thousands. You know, we have field buses. So the technology and the advances in electronics and the availability of high-speed processors has really changed robotics and the application of robotics.
Well, this idea of collaborative robotics, what does collaborative robotics mean, and how has that developed?
Collaborative robotics really is a robot and a human working side by side. So they're collaborating. So in order to have a robot next to a human being working, you have some obvious issues there, and one of them is that the robot could hit the human and injure them. And so when robots are collaborating with humans, the safety systems that have to be put in place are very, very important. Our two-arm robot that we have, that is an inherently safe robot. And by inherently safe, I mean that if somebody were to misprogram it, and it were to hit you, it wouldn't hurt you because it can't develop enough momentum, right, to hurt you, and it's sort of soft, you know, so it physically can't hurt you. So it's inherently safe. But we have new safety systems that we've developed and are available right now. Like, for example, the product SafeMove, that is recognized and certified by independent safety certification organizations to be safe in an environment where humans are there. We have volumetric sensors where it can detect someone going into a cell, and depending on how close it gets to the robot may slow down. If the person advances any further towards the robot, it has a zone and it says, well, I'm gonna shut down completely. So our safety systems are way more advanced than they used to be in the past, allowing this collaboration to occur. So, in short, collaboration is a robot and a human working side by side to do an operation.
Now, I get, humans can react quickly to unexpected happenings. So when robots think, do they think the way that humans do?
No, not really. A human wrote the logic, and so the robot is executing sequential logic. Now, what we're doing more now than ever before is we're applying multitasking operations. So multiple things are happening at the same time, but the robots are able to get sensory input. They're able to search for an object, recognize how it's oriented and pick it up. It's able to get force feedback, so it knows how tight to hold on to it.
Sense of touch.
Yep, sort of like the sense of touch. But there are even new methods where we're having the robot sort of understand their surroundings and operate on something with its own sort of level of understanding of what it needs to do next without necessarily going through any sequential logic. But by and large, these are just like writing a computer program, very similar to that, where there's someone said if this then this, if this then this, right? And if this happens, pick up that tool and do that. So that's the way a robot right now, the classic robot, thinks.
Well, there's so many different things a robot can do. When we look at all these robots behind us, are they all the same robot, just programmed to do different tasks?
No, there are general purpose robots, and then these are a 4-axis packaging robots. It's completely different. You notice it stays horizontal all the time.
Right.
We've got a Delta robot over there for high-speed picking. And then we've got the 6-axis anthropomorphic robot, which is generally what you see in industry, in automotive, and also outside of automotive. It's an articulating arm with the 6 degrees of freedom, and then you have the redundant freedom arms, degree of freedom's arm, like 7th axis. So it sort of goes beyond, above and beyond. But there are really several types of robots that are currently used in manufacturing, and it's the 6-axis, 6-degree, freedom arm. It's the packaging arm, the Delta arm, and then you got the SCARAs, high-speed SCARA arms. Those are primarily ones inside, out of painting, that is.
Right.
Painting robots are a whole other area of robotics, right? There's a whole technology that you apply for painting, and a lot of that is in the process. The way we design the robots really helps the process of painting by allowing, consistent ack and deck and things like that, so you waste less paint. So there are different types of robots for different operations.
Right. Well, obviously, even robots have limitations such as their strength. And so what happens when the robot encounters something that it's just not capable of doing, such as lifting heavy objects?
Yeah, if the robot encounters an object that's too heavy for it to lift, then you sort of have to go back and rethink how you designed the application. But in short, if that should happen and a robot comes across a payload that's too heavy, there are diagnostics that are running all the time in it that sense that, and the robot will shut down, and it'll tell you what the error is, joint collision or too much load. But when we apply the robot, we know what kind of loads it's going to be dealing with, and our robot has the ability to sense the load out there and then configure itself for the heaviest load. Our robot will slow itself down when it encounters a heavier load than when it's operating, the same robot operating on a lighter load. It'll speed up on a lighter load.
Mm-hmm. Well, tell me, can we even think of robots in terms of like human lifespans? Like, do they have a lifespan, and is it comparable? How would you measure a lifespan of a robot?
The lifespan of a robot, it's a hunk of steel. Right, and it's motors and gearboxes. So when major components start to wear and fail, the robot is effectively considered to be at the end of its life, if that's sort of within 20 years. But there are companies that have been using the same robot for well over 20 years, And if you keep the maintenance up on it, and if the parts are still available for it, which usually is going to be the case, they're going to run out of parts, because they obsolete the parts. It doesn't make sense to keep making them. So when there's no more parts available for the robot, then effectively it's at the end of its life. But robots in manufacturing, we expect them to last 20 years at least.
The robots have been getting better and better, and one area of improvement is the robot's dexterity. So as you look at some tasks that humans do, how do you evaluate whether or not that's a task that a robot can do?
Yeah, for typically the conventional test is if a human can do it, then a robot can do it, and probably faster and more consistently. But that's the arrogant answer for a robot guy. You look and see if it makes sense to apply this sort of automation and the kind of tooling that a lot of the costs of doing an application are not maybe in the robotic arm itself. It's in the end effector and the design of the end effector and the manufacture of the end effector. So the way I look at an application, if it can be roboticized or not, is it something, if it has to be picked up, is it presented in a way that can be picked up? Do we have to sort of redesign the way it's presented to the robot? Is it something that the robot, it's not harmful to the robot environment, like obviously, some kind of acidic operation or something where there's, fluid splashing on it, but of course the human wouldn't be there either, right? So generally, if a human is doing the operation, most of the time a robot is going to be able to take that operation over.
Well, actually joining us now live is Bill Leiden from Automation.com. He was here on the showroom floor, and Bill has a couple questions for you. Bill, if you don't mind standing here and grabbing this mic.
No problem.
Thanks for joining us here
Thank
today.
You. Nick, I was going to explore a little more. Traditionally, we've seen the automotive industry was the early adopters of robots, and semiconductor to some extent was the second, I think. But what other areas do you see expansion of robots? What other industries are picking up on it and using them today?
Yeah, you're right. Automotive they were the first sort of manufacturing concern that took over robotics for obvious reasons. But we're seeing robots expand in all kinds of other areas, like aerospace, of course, and even in the entertainment industry is using robotics. The film industry is using robotics, and obviously in painting, but that would go with the automotive. So anything that needs to pick something up, even grinding and machining operations, or what we call pre-machining, it's not a CNC machine, but we have very, very stiff robots like the 6660 that can be used for grinding to a pretty decent finish. Back in when robots first started, you would never consider a robot to grind anything. Well, we didn't even back in those days talk about accuracy. Now accuracy is a very common word to use. It's normally repeatability that makes a robot work. But we also have to watch the accuracy because a lot of the programming is done offline. So when we tell a robot to go 100 millimeters, it needs to go 100 millimeters, or we have to calibrate that some way. So we're seeing robots branch out into a lot of pick and place, food industry, packaging, even the freezers applications, salty snack applications.
Excellent. Behind us are some pretty big robots, and traditionally robots have taken quite a bit of mounting space and very rigid mounting.
Yeah.
Are there some smaller, more flexible robots with maybe some other options today for mounting?
Well, the footprint of a robot is very important to us, and we concentrate very much on how much space that takes up. To me, we've gotten to the point of diminishing returns, right? The robot itself, its arm is covering more than the footprint. So that was a big concern of ours in the design of robots. So I think right now we've gotten to the point where the space that takes up is minimum. The very high power to weight ratio of motors has really come a long way in making robots more applicable to picking up heavier loads and things like that. So the arm can be lighter, so therefore you can get that extra payload. It's a zero-sum game. You get that extra payload out where it needs to be, out on the end effector.
Excellent. Well, thank you.
Great.
Chris?
Thank you so much, Bill. Thank you. Nick, thank you for joining us today. That was a very interesting conversation. I appreciate you coming out, being part of the Brainy Bunch.
You're very welcome.
Then again, we're live here in Orlando. We'll be back at 4:30 with Cal Langton talking about electric vehicles. We'll see you at 4:30. Thanks a lot, everybody.